talk today is about some application of Bayesian network in a specific context, which is dependability, reliability, risk analysis. And at the end of the presentation, I talk about the prognosis problem and the diagnosis and control of systems. So of course, it's a work. Is a lot of people in our lab. So we are interesting we focus more attention on the industrial critical system, particularly energy production, food production, water distribution, drinking water distribution, or chemical process. So here, the battery. So you can see a different partner, industrial partner, or university. So in this kind of system, we have several ways to act on system. We have some action in risk assessment concerning prevention, protection. Some other action through a maintenance loop or reparation, and some other in a control loop to control the system. So each action is based on decision making. So we use measurement, we use historical failure event to compute some information to decide, for instance, in maintenance, and so and so. Some loops are very close to the technical part of the system, as control loop, but others are concern human factor, organization, and very large view of the system. The problem statement for research is that nowadays there are very few interactions between all these kind of loop. And so there are few no verification that the action in one loop are consistent from the other. So the challenge is to extend the life of the system, to ensure the safety, to manage the risk in the case of failure or degradation of the system, and to optimize the control action on the system. So the problem is to use a model in which we base the decision making, and our objective is to use this kind of model to model the impact of the control on the health of the system, to model the impact of the maintenance on the availability of the system, and to model the impact of the operating condition on risk about the system. And our idea is to focus on a specific model, language, okay, to describe all the combination of system states, functioning, dysfunctioning states, and multi-component states, and of course we need to use a probabilistic approach because some events on the system are not known, and we can only know probability distribution, probability measure of this event. So we focus on probabilistic graphical model. This kind of model allows to model the joint probability of the global system view as with all the states, and it's able to manipulate all the multiple states view of component in the model. That's right. So my presentation is divided in two parts. One on a static modelization. The static view is how to build model in dependability or risk analysis. I can show you a short application in risk analysis. And the second part is about the dynamic view that take into account temporal evolution of the system. Okay. Okay. To understand how we philosophy, I have decided to use this very short system, technical system with 3 valves. So each valve has 3 states. States OK, the valve is OK. We can open and close the valve. The state remain closed is that the valve is closed and we cannot open the valve. Okay. And the valve can remain open. We cannot close the valve. Okay. The objective, the mission of the system is to control the flow through the system. And so we can define the variable that defines the state, the global state of the system according to this mission. So we can say that the system is in the success, have a success of its mission, or we have a failure of this mission. You can imagine that we can break down the system in several functional parts. So we can imagine that we have a stage E1, stage E2, and we can use variable to describe the state of this stage. Okay. So in this very short, very small system, we can have a look to the joint probability law that combine all the variables. Okay. This joint probability is very interesting for us because if we want to know the probability that the system is in one specific configuration, we can use marginalization. But the problem is that, of course, for this very small system, we have a lot of probability. Okay. And in dependability or reliability, the objective is to know if the system satisfies the objective, the mission. So we have just to marginal the disjoint probability according to the fact that the variable f is in state OK. So we have the probability that the system is OK. As you already know, we can use conditional independency between all the variables to describe this joint probability. And the Bayesian network is just a representation, a graphic representation of this equation. So by this way, we can define a very compact model of this. And what is important is that by inference we can compute the probability of each variable, we can add information, propagate this probability. So for this situation we can have a diagnosis on the component that allows that we want to control the system, and we can add some other observation, and we have a view of what happened in the system. So, the problem is how to build this model. We have difficulty to define all the probability, the joint probability, because we have not, of course, all observation. So a way to model this kind of system is to focus on the success scenario or on the system. So in this very small system, we can define variables that explain a scenario of functioning. If the variable is equal to 0, okay, the scenario is available. If the variable is equal to 1, so the scenario is unavailable. So here's 7 scenario of functioning of the system. Okay. Okay. If the component x1 and x2 is in good state, everything is okay. We don't care about the state of component 2. If we have this scenario, if the component 2 is open, the valve is still open, we cannot close, we can use the component 1 to control the system. And we don't care about the component 2. Okay. This allows to build the structure of the model. Okay, we have connection between each variable to each component. And of course, the global view of the system is if there exists one scenario of functioning, it's okay. Okay, we can have a more compact view by union of some variable. This is one model. Another way is to, okay, we can compute everything we want by this model. We can compute or find a structure with another strategy. We can focus on the scenario of failure on the system. So in this case, we define some variable C, in which C equals 0 if the failure scenario is available, exists, occur, and C is equal to 1 if we have occurrence of a failure scenario. So if the component 1 is in state 1, yes, 1, it means that the component is blocked and closed, so it's a scenario that in which you cannot control the system. Okay, and the same for the rest. So we have another structure of the model. That exactly the same thing, but we have built the model starting from not unfunctioning state of the system. Failure scenario. We compute exactly the same distribution of probability on the global view of the model. Another way is to use a functional decomposition of the system. If we are able to describe the system with several functions, you can say, okay, this function, if this function is satisfied, it's satisfied a part of my system. If all the functions are satisfied, it's okay for my system. So we can imagine in this very small system that we can break down the system in several functions, the function to circulate the fluid, and the function to stop the flow. It's dependent on flow, and all these two functions are break down for the sub-function, which are connected to all the components, V1, V2, and V2. Okay. So we are a way to structure our mind, and we can map to all this flow variable of the Bayesian network. Okay, for the global view with two functions. The first function results in L, the variable L, and the second is the variable I. And the system, the global view of the system is Y. Okay, with okay. In this view, we have the circulate the fluid functions. So we have break down these functions in 3 variables that depend on the state of the component. So the same for the others. And so we have another model that computes exactly the same. Okay? So, okay, we have several methods to build model with different view of the system. Sometimes we are interested to know the functioning states. Sometimes we are focused on failure scenario or other based on the functional decomposition of the system. Each model are the same objective. This is what we explained to our student, and it is explained in the first part of this introduction. Now, application in real context of industrial context. You are focused on the problem, which is risk analysis with our partner EDF, which is a French electric power provider, particularly nuclear power plants. Okay. I focus in some evaluation of how a safety barrier acts on the risk in this kind of very complex system. So here is some application. What we do? We have analyzed the organization of the staff. Okay. We analyze the team who have action on the system. We analyze the technical part of the system with Gucci, which is a failure propagation in the system and consequence propagation around the system. And we analyze how organization, action team act on the efficiency of each barrier on the technical part of the system. Integrate some action and interaction with the environmental condition. Some are regulation, administrative constraint, or natural environment condition of humans. Okay, you understand that if we work on this knowledge structuration, we can then map a Bayesian network that define all the flow between each function. In the same spirit that I have explained in the very small system just before. So in this case, we have this analyzed, and so we define a model, a large model in this case, like that, to compute the risk map. Risk map is the combination of frequency and gravity of probability and gravity of events, critical events. So when we use Bayesian network, it's very interesting because we can use inference to backpropagate the information in case of critical events, and we can see from which variable the problem comes. And so we can have some modification of the organization, technical part. Okay. Now the dynamic view of the system. Okay, in dependability or variability, you can describe the system by several states. Some states are concerned the functioning state, others are concerned failure state. In functioning stage, we have degradation, and good state of the system. This model result in if we have some condition on the probability of transition between all the states, we result in the Markov chain. So we can solve the differential equation to have the solution. Okay. Dynamic Bayesian network is interesting because we can model each state of the system in one variable, and so we can enroll this variable around the time. Okay. So if we can have a propagation of the state according to time, 0, 1, 2. If the conditional probability table in each variable are the same, constant in time, so we have a Markov chain. And we can use this very compact model available in BayesiaLab. So we have only just to define this conditional probability table, which is nothing else than the probability of transition between states of the system. States 1, 2, 3, 4. As in this example, 1, 2, 3, 4. Okay. Now, in reality, from where come the parameter? In fact, in a very simple case with one component with two states, we are interested in the parameter which is called the failure rate. Failure rate is the probability, is used to compute the probability of jump from a state OK to a state down. And we can use database to estimate the mean time to the first failure, okay, which is here MTTF, to estimate the probability in our conditional probability. So here is the evolution of the reliability of one component. It's a very simple system process. Of course, it's not the reality, because in real context, the evolution of the component depends on the operating condition. Okay. So we can imagine that we have a variable that describes the situation as different operating conditions. Okay. And if we have this variable in stage alpha, we have a specific operating condition, so we have a specific conditional distribution, transition between each state of the system, the component. Okay. In BayesiaLab, in Bayesian network, dynamic Bayesian network, it's very simple to model this kind of process. So, okay. We have just to add a variable u, and in this conditional probability table, we have the two matrices that define the two components, the two compartments, the two behavior of the system according to the exogenous variable here. So we can see that before to change the environment, the functioning condition of the system, we have a very slow degradation of the variability. So we have a quick deviation of variability after change of condition. In reality, we have a more complex system, process, In fact, you cannot observe the real state of the system. It's a hidden process. Cannot observe it without opening the components. Okay, right down the system. So it's a hidden process, but we know the condition, the operating condition, okay, that have an impact on the process, and we observe some consequences yes, of this, the state of the process propagate through the system function. Okay, if we connect the view in a static view, I showed in the beginning of the presentation, with this dynamic view, only in one component, we can now imagine that we have a fusion of information coming from several components with very complex process, input-output hidden Markov model, which is the most complex view, Markov process, perhaps with several hypotheses, or semi-Markov process. All this extension is possible with BayesiaLab. So now, application to the system. Okay. I show you an application on the small system we have used, I think, with a 3 valve. Okay. If you want to build the Markov chain of this kind of system, well, all the combination of these 3 valves, there are 3 valves with 3 states, so this leads to 26 states. So the method I present allows to build another model based on that part on dynamic Bayesian network, part of which is a static Bayesian network, and in this model can compute everything we want as it's possible in Markov chain. So we have an equivalence, and the difference is only a factorization of the view of the model in this representation. Okay, now if we have a more realistic system, you can imagine this water heater physical process, okay, with several ways to heat the water, pump the water, some sensors. Okay, we break down the system in the functioning analyze. Okay, we define all the flow between each function. Functions are dedicated to control the system, to measure the level of water, and so on. Okay, so we need some information to define all the states of this flow. So we have some analyze, which is called failure mode and effect analyze, that analyze all the deviation of the flow according to the state of component. We can see that each component can have a dynamic process model as Markov chain, for instance, with all the mean time to the first failure parameter I explained before. Okay. It's impossible to define the Markov chain of this global process. Okay, it's possible, but it's very difficult. But if we map each view, each knowledge is a method I explained, so you can build this model. Each here is can find each component, sensor, computer, valve, tank, water pipe, heating resistors. So here we have the energy, electric energy, and the function to function on the system. So this is a global view that allows to compute reliability, availability of the system. Okay. Now an application to away with the objective of diagnosis and prognosis on this kind of system. Okay. It's an application on diesel generator that provide electrical power input. So the objective is to diagnose the state of the system, to prognose the future state of the system in order to define maintenance action when the talk come back to. Okay, what is diagnostic or diagnosis? Diagnostic is to define the state, the current state of the system. When we look at the system, we want to know what happened in the system. The prognostic is to define what is the future state of the system. Okay? So we get this dynamic view of the process I explained before. Okay, in this application we are focused on the hidden Markov model. We have the hidden process that describe the state of the generator, okay, and some observation. Okay, in this example, we focus in one observation, the temperature. Temperature. Okay, so we have some signal processing analyze of sensor on the system, and so we have some treatment of observation, and then we use this observation to compute the model of the system. And after that, we use this observation to compute the states by diagnosis or prognosis of this. So there are several states, two states. One to identify the parameter of the model, and the other to use the model to make the diagnosis and prognosis. Okay, the observation is the evolution of the temperature. So we use discretization of this temperature with some, according to expert judgment, okay. Okay, part which is okay, normal situation, medium temperature and very low temperature, and some other in which we can see that we have some degradation and very high temperature that leads to failure of the system. So critical situation. We use this structure of model. Okay, we have okay, we can imagine that we have three states to describe the state of the component, the diesel generator. Okay, one stage you can imagine the normal functioning. The second state is a degradation situation, not really normal, but the functioning is okay. And the stage 3, which is critical situation. So we have observation, the conditional probability table that link the observation and the state of the system. So the state of the system is propagated to the observation. Okay. So we have observation defined from the state the system. So this, for the learning, we use expectation maximization algorithm to define all the matrix, transition matrix, which is the dynamic evolution of the process which is hidden, and the emission matrix, which is the connection between the observation and the state, the hidden state. Okay. So, after that, we have some diagnosis, operating condition. We have some observation during this first part. Okay, so observation O is here, and we compute the probability of X knowing O, the observation before the date T. And the objective of diagnosis is to define the distribution of X at the T instant. Okay. So in our analyze, we have which will depend on the quantity of measurement. Here is the diagnosis, and the other is the prognosis. The idea is to observe the variable temperature during windows, okay? And now we have, of course, the diagnostic at time t, and we want to compute the evolution of distribution of probability of x at time t plus 1, t plus 1. Okay. Here is the performance we have, okay? More we are far to the observation, of course, less we are efficient. Okay. Here is another application of dynamic Bayesian network. Now, application in control. We want now to control the water distribution in the town. Okay. So we have several tanks with drinking water and several pumping station. Here, P1 to P9, P10. Okay. And here is some sources of water. So, as you imagine, the consumption of water is a cycle repetition day after day. Okay, we are, of course, integrating, we want to integrate the reliability in our control strategy. Reliability is the view of the evolution of the ability of a pump to be able to function. So, we have here the system, and here is a control algorithm, which is based on the optimization part. Okay, and in this optimization, we need some parameter to choose what is the solution we can use to pump the flow of water and to satisfy the objective, which is given in this variable. Okay, so of course you understand we can pump through X2, pump by P6 through X1, and then we have water. But another solution is to pump by P4, take X3, X4, X1, and then we have water. Okay.
So there are a lot of different scenarios of control in this kind of system. So the question is, if we have some degradation of this pump, is it possible to use other strategy? Or perhaps is it interesting to preserve or to destroy the pump and be sure that we have another solution after the failure of this pump? So we don't know how to do that. The way to do that is to compute the sensitivity of the global reliability of the system according to the pump use or operating condition. Okay. How to do that? When we know how to control the pump in the system, then we compute here the failure rate according to the fact that the pump is used or not used or used over the normal condition. So we have the level of failure rate. And we use this failure rate to compute the global reliability of the system in the dynamic Bayesian network. And we compute by inference the sensitivity of the global reliability of the system according to each component, each pump function situation. So we have for each pump the sensitivity that allow to choose what pump we use on the control strategy. Okay, so here is dynamic Bayesian network, exactly as I have presented before. Just a little difference here in the conditional probability table. We have a parameter that depends on the fact we use or not, or the condition we use the pump. Okay, so it's a semi-macro chain. The probability is not at each time the same. It's dependent on the configuration. So we use this model to compute the sensitivity of the global view of the system according to each component, and we use this control optimization loop. So we have tested several ways to do that. Okay, in one way, we don't care about the reliability of the component. Okay. The second, we are focused only on reliability of each component without a global view of the reliability of the system. It's not a sensitivity analysis. Okay? And the two others are based on the sensitivity of the global reliability according to each component. So we have several situations of functioning on the system. The strategy is completely different according to these four situations. Now, if we look at the reliability, the global reliability of the system, the classical strategy is here, the reliability is decreased. And if we take care about the sensitivity of each component, we change the strategy according to the degradation or the failure of component, and so we conserve a very good level of reliability of the system. Okay. Of course, in this example. Okay, it's time to conclude. Yeah. Okay, I show you how to build a very big model of a system. Okay, it's a technical system. Perhaps sometimes we integrate some organization, human in our model. Okay. The thing which is very interesting in Bayesian network is the multi-state ability in each variable. We have not this kind of ability or facility with other kind of model techniques. And I show you how dynamic Bayesian network can be used with a very complex process, Markov and semi-Markov chain, Markov switching model, hidden input-output hidden Markov model, and so on. And what is very interesting is the ability of factorization of the dynamic Bayesian network to build very complex model, but finally very simple, with a very simple way. So it's very interesting. So here is our small contribution in this challenge, which is how to manage all the view, all the action on very complex and critical system by using, probabilistic model. So thank you.